In section 7.4, we take a look at separable equations, that is, separable differential equations. A differential equation is said to be separable if it can be written in the following way. A function of y times dy dx is equal to a function of x. So in other words, you can separate all the y's on one side and all the stuff with x's on the other side. As an example, consider the differential equation dy dx equal to x cubed divided by y squared. So if I want to see if this differential equation is separable, I'm going to ask myself, can I do a little bit of algebra to move all the y's on one side and all the stuff with x's on the other side? And in fact, if we take this equation and simply multiply both sides by y squared, I get this to be y squared dy dx is equal to x cubed. So on the left hand side I have this sole function of y, and on the other side I have this sole function of x. So in fact, this is a separable differential equation. As another example, suppose that you have dy dt is equal to, let's say, square root of t e to the y. So the variables are a little different. Instead of an x, we have a t, but the t takes the place of the x, right? So you're asking yourself, can I move all the stuff with the y over to that side and all the stuff with the t over to the other side? And here, simply by dividing both sides by e to the y, so 1 over e to the y dy dt is equal to the square root of t. So on the left hand side I have a sole function of y, and on the right hand side I have a sole function of x. So in fact, this is a separable differential equation. So let's solve these separable differential equations. Let's take this example that we have here and solve the differential equation. So I'll introduce it as an extra problem, and here we're asked to solve the differential equation dy dx is equal to x cubed over y squared. So what you're going to do is what we did above. Move all the y's one side and all the x's to the other side, so that we have in front of our dy dx a y squared, and on the other side an x cubed. But in practice, if we want to solve these differential equations, we're going to go one step further, and we're going to think about our dy dx almost as if it were a fraction. Now, technically this is not correct, and there's some calculus to validate our steps. We're not going to go through that validation. We're just going to go ahead and use this shortcut. So we're going to think about this dy dx as if it were a fraction, and I'm going to multiply both sides by dx to get y squared dy is equal to x cubed dx. Again, in terms of calculus, this isn't 100% correct, but there's some calculus that tells you pretty much that the steps that you do by going through this technique give you the same answer if you did it the more formal way. So this is a huge shortcut. And this method is a method that you'll definitely see in your physics classes, so it's worth being exposed to it right away. So on the left-hand side, we have a conversation about only elements with y's. On the right-hand side, only elements with x's. And what we're going to do is anti-differentiate both sides. On the left-hand side, anti-differentiating with respect to y. On the right-hand side, anti-differentiating with respect to x. The antiderivative of y squared with respect to y is 1/3 y cubed plus a constant, let's call it plus c1. On the right hand side, we have the antiderivative of x cubed to be 1/4 x to the fourth plus a constant, let's call that c2. This c1 and this c2 we can combine together. Let's say I've subtracted c1 from both sides. Then I would have 1/3 y cubed is equal to 1/4 x to the fourth. And instead of writing c2 minus c1 here, I'm just going to say plus c, where this plus c is an arbitrary constant. It's just some constant. I'm not really, I'm not sure what it is, and I really don't care what it is at the moment. Now, we're almost done here. Our job is to solve for y if we can solve for y. In this equation, would you be able to solve for y? Would you be able to isolate y from the left-hand side? Well, let's get rid of the 1/3 by multiplying both sides by 3. So we have y cubed is equal to 3/4 x to the fourth plus, and when I take this arbitrary constant and I multiply it by 3, I'm going to get another arbitrary constant. So a lot of times instead of writing 3c, we recognize that this will give us another arbitrary constant, a constant that really doesn't matter at the moment. So oftentimes you just rewrite it as a c. This is called abusing notation, when you rewrite a variable to represent different values. We're almost done. We just need to get rid of that cubed by taking the cube root of both sides, and y would be equal to the cube root of 3/4 x to the 4 plus c. So this is the function that we can plug into this equation over here and satisfy the equality. On the left-hand side, we would be taking the derivative of this function. On the right-hand side, we would be taking x cubed and dividing by this function squared. And this is again, the function that satisfies that differential equation.